Hello, I am Pascal Seiler, member of the Joint Lab for Signal Photonics between IHP and Technische Universität Berlin, and today I have the pleasure to take you with me through the characterization of our high-speed optical coherent receiver. The coherent receiver we will present to you today is a novelty. It is a monolithically integrated high-speed C-band coherent electronic photonic subsystem supporting up to 64 gigabaud. It has been fabricated here at IHP in our 0.25 micrometer photonic BiCMOS technology, which monolithically co-integrates bulk silicon high-speed RF front-end electronics and silicon photonics. This allows us to bring electronics and photonics together on a single chip, reducing the impact of parasitics and improving the performance. A monolithic integration also reduces the cost for packaging and assembly. In the next few minutes, we will take you with us to a measurement session. Together, we will characterize the coherent receiver in a back-to-back noise-loaded environment. Before we can begin the measurement, we have to prepare the setup. This is a time-consuming process, but don't worry, we sped it up quite a bit. Characterizing the receiver actually requires a system experiment. Thankfully, I got some help from my colleague Anja. This makes the entire process much easier and more reliable. To test the device on wafer, extra work is required in comparison to a conventional setup. This is mainly related to using a semi-automated 300mm prober that necessitates optical and electrical probing instead of fixed connections. For the receiver, we place DC probes on the north and south side of the receiver, delivering supply and control voltages for the RF circuit. A high-speed RF probe on the east connects to two real-time oscilloscopes. The fiber array on the west side is connected to a noise-loaded transmitter and to an additional laser source for intradyne signal reception. Good DC and RF contacts are crucial, and checking the probes beforehand is mandatory. The prober automation, precise wafer-level alignment and 300mm probing capabilities are major assets here at IHP. This enables wafer mapping of functional tests, and it allows us to characterize receivers in quick succession. Now we are nearly done with the heavy lifting and can continue to the actual measurement. We now have a setup as you can see it here. On the transmit side, we rely on an arbitrary waveform generator and an external IQ modulator for generating our 64 gigabaud signal. By loading the optical signal with amplified spontaneously emitted noise from a fiber amplifier, we can emulate the effect of multiple fiber spans of signal refreshment. The effect of added noise on the signal is clearly identified on the optical spectrum in form of a rising noise floor. All measurements and adjustments are done remotely. So now I'm going to share my screen with you. First, we start with a comparatively low symbol rate of 20 gigabaud to verify the end-to-end signal quality and optimize the offline digital signal processing. From the recorded symbols, we first recover the clock frequency and the carrier phase, which are not available on the original data due to the intradyne mixing and phase noise originating from the different optical sources. Afterwards, matched filtering and equalization are applied. After the signal processing, we obtain the recovered constellation for our 20 gigabaud signal. The bit error rate is shown on the bottom. The transmission is presently error-free as we did not add any noise yet. For the highest performance, we are now increasing the symbol rate to 64 gigabaud. At this symbol rate, we will perform the noise loading while determining the bit error rate for the varied optical signal-to-noise ratios. For a low level of added noise, the constellation remains clearly visible. We can now raise the noise floor. You can clearly see the change in the constellation by a rising bit error rate. Using this method, we can estimate the capabilities of our coherent receiver to handle severely impaired transmission channels. With the characterization of our optical coherent receiver, we can evaluate its performance and compare it to other state-of-the-art devices. Today, you have seen the result of our specific model of collaboration. Under one umbrella, we can combine design, prototyping, wafer-level engineering, and advanced testing. With this, I thank you for your attention and see you next time here at IHP.